All right. So thanks a lot. As you've heard, my name is Milan Ondrašovič, and I would like to talk about vectorization, which is quite an important topic in modern computing. So what do we need? So what do we need for that? Basically, knowledge of Python. That's obvious. But then you also need NumPy. The more you know, the better. And some fundamental grasp of linear algebra. Nothing serious, but just to have an idea about matrices. So speaking of vectorization, what do I mean by vectorization? Basically, it's about writing code to utilize vector operations that enables you loop execution in optimized way. For instance, in the low-level languages like C or Fortran, then you can leverage SIMD instructions, which stands for single instruction multiple data, for basically enhancing your computational efficiency. So for me, that would be like avoid loops unless necessary. What do I mean by vectorization is this, but it's not about image conversion or matrix transformation in this case, even though we're going to deal with matrices for some time. So let me motivate you with a really simple example. We're going to compute the sum of squares of multiple numbers. And here you have a definition of a list of n real numbers, and then we just square every value and sum them together. That's it. Here's a pure Python implementation, basic loop over the values, sum them up. Then there's kind of improved, more concise implementation using comprehensions. I would even personally say that try to adopt comprehensions if you can. They are often concise and faster, except for several cases like this one, but that's not the point. And here is the vectorized implementation. Again, in terms of brevity, it's on par with the comprehension-based, but it's slightly different when it comes to the speed. Here are the results of the benchmark. I mean, you get the gist. Like, we don't need to talk for too long about what it means. Basically, a simple benchmark, and you see that with growing input size, you get tremendous speed benefits. That's obvious because there are some underlying mechanisms that allow you to do that. In this case, the comprehension is actually slightly slower, but that sometimes happens for reasons that are outside of this talk. So there are several common use cases. Vectorization, I would like to emphasize that it's quite a general idea. You shouldn't look at it as just some library tool, but more of a skill that you can learn and apply across different range of libraries. For example, NumPy, PyTorch, TensorFlow, and then there are many libraries built on top of these. For instance, OpenCV scikit-learn, scikit-image, and you also saw that slide that all of those projects that are sponsored, a lot of them harness the power of vectorization. To me, this is quite a personal feeling. This is by no means a general statement. It feels like working with some domain-specific language. Like when you try to do some vectorized code, it feels like that. And why is that the case? You have conciseness and expressiveness. Basically, you deal with some high-level abstractions. Then you also need a shift in perspective. And that requires you to have some array-oriented thinking, and obviously a standard tooling, a set of tools that you just assemble to have your final solution. So that makes me think it's like working with a DSL. There are various roles that actually exploit the vectorization. For example, basic programmers for numerical computing, data scientists for data processing or exploratory data analysis. And my favorite, since I'm a machine learning research engineer, that's the machine learning, model training, and inference. So once you adopt it, what does it mean for your code base? There are several impacts. I have chosen these three, like execution, implementation, and code base. So when it comes to execution speed, you can gain even 1,000 times faster execution. Then you have parallel instructions execution under the hood without you having to do anything about it. Sometimes when you use it improperly, you might actually end up with slower code. That's really rare. You have to do your best to achieve that. and obviously some longer loading times. For example, TensorFlow, you might end up with several seconds just to load it. And if you adopt it in unit tests, it's quite a huge problem. So these generally hold true, but some exceptions exist. Then you have transparency. For example, some libraries that allow you to execute the code on top of CPU or GPU, again, in a pure transparent fashion. However, there are some, like PyTorch, where you have to specify explicitly whether you want to run on CPU or GPU, as you can see on this example here, where you have to transfer the data between these devices. If there are some mega guys, then you, for example, might use the Torch device MPS, which stands for Mellow Performance Shaders, but that's out of the topic, just for reference. Data types. This slide is kind of interesting. Please look at the example that I want to show you. You have some internal data type specific optimizations. So for example, if we look at this example here, we create a simple Python list containing 2 elements, and then we override the first element with a string. Obviously, under normal Pythonic assumptions, this will work. However, if you deal with a NumPy array and you override it, it gets truncated. And the reason is that the NumPy array is a contiguous block of memory, and during the initialization, it actually determines that the longest string has the length of 3. Therefore, everything longer than that will get truncated. And if you don't know about it, how to debug this? Like, it's quite difficult to find the root cause of your problem sometimes, and it might be quite tricky. So these optimizations are there, and you need to be aware of them. Code behavior. Obviously, this code behavior is expected across libraries, which is an advantage. It's actually also less error prone if you know what you're doing. But some assumptions might be quite misleading. And oftentimes, when you end up with some internal errors that arise from the depths of C or C++, they are essentially unreadable. So if you let me paraphrase the giant Donald Knuth, I would say that built-in optimization may be the root of some evil sometimes. You know, let me give you another example. Here we're going to talk about views versus array, but that will be topic also even later. When you slice a list in standard Python, that creates a copy. Therefore, if you end up modifying the list, you do not touch the original data. That's not true with NumPy arrays, since they are quite optimized, and they try to create a view. Therefore, any optimization that you do to your new array ends up being projected to your original data. So you just override the original element. So it's better to assume that you're working with a view unless proven otherwise. Maintenance and portability. You're outsourcing your computation to an external library, which is quite good. You don't need to care about many things. Even porting between libraries is quite painless oftentimes. But if something goes wrong, then it's pretty bad, and you don't want to end up in that situation. So you have a dependency, therefore all these conflicts during dependency pinning and all that, which is quite similar to maintenance, especially when you need to bump your versions. So I would even personally say that there is some fine line between vectorizing and obfuscating your code. Readability and onboarding, the brevity can be a blessing, but at the same time, it can be a curse. You have easier knowledge transfer, but I would say that even a seasoned programmer might feel like a newbie, because if you don't know what these vectorized instructions and essentially these vectorized functions do under the hood, it might feel quite, does it really work? I mean, this is impossible. So let me finally go for something more interesting, which is quite a fundamental concept in vectorization itself, and that's broadcasting. It stands for broadcast to a smaller array across the larger one in order to assure some shape compatibility. So if you want to simulate this effect, you might actually use the NumPy broadcast too. But It's about the concept itself. I would even say that it's so important that some mathematical books, for instance, this deep learning book by Goodfellow, Benjo, and Kerviel, they adopted the broadcasting notation to simplify the formulas in this book. I mean, it's against the rules of linear algebra, but it's just really neat. What it means that first, you are operating on two tensors on the input, and you go through the phase of shape alignment. There is some left padding, and then you proceed along every dimension starting from the end and just compare. All right, are they equal? If they are, fine. If they aren't, if one of them is 1, then it gets stretched to match the opposite dimension. Otherwise, an exception is raised that the shapes are incompatible. If it looks like it's confusing, let me show you an example here. If we broadcast a 1D array, we go like this. We have a vector of shape 3 of length, and then we are going to multiply it by a scalar. Scalar has like no shape by default, no dimension. So what you go through is the first stage, and that is the alignment. So you go from a scalar, 0 dimension, into something which has a dimension of 1, and there is just one element in it. And then there's the stretching. So you compare all your dimensions and you see, okay, this is just 1, so let's stretch it to match the opposite dimension. And you end up multiplying 2 arrays, basically, 3 by 3, which is actually not true. It's not happening. Obviously, no copying of elements. It's just tricks on the level of loops down under the hood in the implementation of library like NumPy and so on and so forth. But it's a general idea how to broadcast your operations to be efficient with them. Broadcasting works obviously in multiple dimensions, and if you have this 2D array, like this one, 4 times 3, and if we do addition of a single vector of length 3, basic linear algebra dictates that this isn't possible. I mean, you can just add elements in an element-wise fashion, and that's the end game. That's the end goal that you eventually want to reach. So how to transform the second matrix, or well, at this point is the vector, into a matrix so that you can do element-wise addition. And here it is. So we go through the alignment, and that is left padding with ones, and then we proceed dimension by dimension and just stretch. So we end up with something 4 by 3 plus 4 by 3. But it's just a trick on the level of loops. No memory overhead. And broadcasting can obviously happen on the level of both arrays. So you get the idea. It can be really quite tricky sometimes when you're just looking at the code. So to make things even more complicated, there's this notion of Einstein notation. This is actually true. In physics, it's used, and Albert Einstein proposed this notation, which is basically a notational convention that implies summation over a set of index terms, and you can achieve some pretty brief notation. For example, if we have here a summation over 3 elements, you have a scalar times some element of a vector, you can simplify it into this ci times xi, and we assume that we are summing over these indices. That's the whole idea. You just assume that there's sum everywhere. So this is pretty concise and efficient method for performing various tensor operations. And you can just use string notation to specify your indexing. But my personal advice would be, if it's possible, adopt standard functions. Don't use this unless you really have to, and there is the benefit. Well, let me show you an example here. We are going to just sum all the elements of this 2D matrix. So what you do, you create this notation and you say, all right, the ith index is going to run over rows, and the jth index is going to run over columns. And the arrow right in there, that indicates just accumulate whatever values you find. And that's it. But it's equivalent to just calling sum directly. You can also do matrix multiplication. If you remember your algebra classes, you might find the index notation quite similar to the definition of matrix multiplication. So we have the ith index over rows of the first matrix. Then, the kth index, these needs to match. So the number of columns and the number of rows, that needs to be identical. And then you have the jth index over columns. And you use them to actually store the value as the ith and jth element. And the k runs basically the summation, which is assumed that it's happening. So you can have pretty elegant and concise implementation if it's needed, but it can be quite difficult to read. You can even do transpose. You just swap them, J and I. You should never use this in practice. For these examples, it's just to demonstrate how it works. For instance, during my PhD, I was working on one cost function, and I was literally using 4 different letters in order to index it. It was quite fast, pretty concise, but for that one-liner, I needed like 20 lines of docstring to explain what's going on there. Einstein notation actually inspired different implementations and different libraries to adopt it at a broader scale. For example, here we have some string-based notation to perform various tensor operations, like rearranging your dimensions. Here you have several different advantages. You are naming your dimensions in the code, so there's just one single source of truth. You don't need to rely on comments, even though we're going to talk about it. And you just see, okay, I'm going to rearrange them and use channels first instead of channels last. Or you can do some reduction over a specific dimension together with swapping both of your dimensions. And obviously some repetition, tiling, and so on and so forth. If you are interested, go for it, look for ANOPS. It's pretty interesting. This is just to demonstrate some basic operations that you can do with it, and they are inspired by this Einstein notation. Here are some other performance tips from me. Whenever you're working with your arrays, make sure that you know your memory layout, the memory order. Here you have row major, which is also called C-contiguous mode, and that's the default. It means that your data is stored along the rows in memory, but there's actually so-called Fortran contiguous or column major, where the data is actually stored in columns. And you can imagine that if you are iterating over your data, you are experiencing different rate of cache misses and cache hits. It depends on in which direction you access your underlying data. So, if you have big arrays, it might be a big difference. So keep that in mind, spatial and temporal locality in terms of memory. And that leads me to the idea of modifying arrays. Arrays are allocated as a contiguous block of memory. That's it. So whenever you are resizing it, you have to copy it once again and reallocate. There is no linked list or something like that. It's a block of memory. So if you are trying to resize it, especially in a loop, please don't do it, and allocate your memory with numpy.empty and then assign values using indices directly. It's not really neat, but it's actually not that extremely slow as trying to accumulate into an array. It's even worse than using it for Python list. And when you are trying to resize your memory, you will more often than not adopt some stacking, horizontal stacking, vertical stacking, which actually internally call concatenate anyway. But then your stacking direction and your memory order impacts the eventual performance. So if you have row major and you are stacking vertically, you know that it's the least painful way to do so. And you can kind of reason through the rest of the table what direction and what memory order are like more suitable. But the impact is not extreme, but it's still there. Here is another slide talking about view versus copy. So when you have an array, when am I dealing with a view and just a copy? So here are several cases. A view is created when you are slicing your array, reshaping it, transposing, or swapping axes in general, and unraveling. And then you receive a copy if you have masked your array, mask selected, or you used fancy indexing to select just several elements without any order. And also when you are flattening. Down there, there's a hint how you can check whether you are actually dealing with a copy or with a view of some underlying array. Then there are also unbuffered operations. This is quite advanced thing, but the notion of universal functions is of paramount importance for vectorization. Why is that the case? Well, you have a universal function that operates on elements by definition. That's right there. It operates on ND arrays in an element by element fashion. And we have a family of universal functions like ufunc_add, ufunc_reduce, ufunc_accumulate, and so on and so forth. Why are they useful? Well, look here. If you access your array using this compound index using a list, there's buffering under the hood. So basically, if you want to increment the first element 3 times for whatever reason, it gets incremented just once, not 3 times, because the buffering under the hood keeps track of your indexing and how many times it accesses a certain element. But if you want to be blazingly fast and don't care, just override it. I'm telling you, just do it. Well, you can have these unbuffered U functions, and they actually provide you the desired result. So this is really fast and it operates in place. Then I would also I would like to highlight that if there's a need, and it should be quite rare, but if you ever need to do so, prefer numerically stable versions of your functions. So if you're, for example, working on some machine learning project and implementing a custom loss function, you might find yourself implementing some exponentiation and then modifying the values. Look for the numerically stable counterparts for whatever you're trying to achieve, and there's a chance that it exists. So for example, here we have some exponentiation and then subtracting 1. You can do it like shown on the left, but actually a lot better solution is to rely on the different function because it takes care of numerical stability, which means you don't end up with overflow, that is infinity, you don't blow up, and conversely, you don't end up with underflow, which is like when you're rounding down something to 0 inadvertently. So how to make vectorization easier for you? Well, this is also my personal cookbook. Try to harness the power of Jupyter Notebook, specifically its interactive mode, because you can do data inspection on the fly, which is really handy. Then try to visualize, use some plotting, matplotlib, and so on to help you understand the data you're working with. And also, you can explore your shapes of your tensors on the fly, which is really useful. So try to expedite your implementation with these tricks and interact with your code on the fly. Then, when you're writing something, think about it in holistic terms And many of these functions, they can be generalized into mapping and reducing. So mapping is basically dimension preserving, whereas reduction means reducing a dimension, literally removing it somehow. So if we just, square every element of some array, we don't change the shape. However, if you do summation over a specific axis, you remove it. If you want, you can prevent the reduction by actually sending keeps dims equals true, but the whole point is you are reducing your array along a certain axis. As a mnemonic hint, whenever I'm trying to remember something, especially this thing like how to, which direction or which axis should I use as a parameter? It's basically the one along which you are doing the reduction. So that helps me to remember it. Then try comment your tensor shapes. Don't use the single letter scheme. I would prefer the full name, variable name. This helps a lot. It's documenting your code, and you can find yourself implementing some vectorized function and having to rely on Jupyter Notebook and on-the-fly exploration quite a lot. And then when you get back to your code later on, you will find yourself quite baffled how the data shapes change as the computation progresses. So just look at the example, don't think about the implementation. But here I'm just showing you that you can jot down in the comments what shape you are dealing with, and it might help a lot with readability. But keep your documentation and comments up to date, because if they lie, it's essentially worse than nothing. Using advanced type hints. If you don't want to rely on comments, you can adopt advanced type hinting to specify the shapes of the data you are working with. It's not very common, but just be aware of its existence. So here is the conclusion where I would like to sum up some key takeaways from this talk. Vectorization in and of itself is extremely useful for performance demanding applications. Basically, remember that the looping that happens under the hood, and it's improved because it's executed in C or Fortran or in some different low-level languages. It has quite a strong potential to vastly improve your solution if you adopt it. Basically, I would even say there is an educational value. If you learn the basic principles, you can easily transfer your knowledge from NumPy to PyTorch to TensorFlow. They are quite similar if you look at the code. There are some differences, and you just have to be aware of them, because you might find yourself chasing some quite nasty bugs. I think it's undeniable that it has become an industry standard, one way or another, and as a result, there are plenty of resources to learn from and quite a solid community support. So I would just say it's just a tool as any other, so don't eat soup with a fork and adopt it when it's needed. So that is everything from me. Thanks a lot for your attention.